it as well. All right. So here it is. Here we'll do a small calculation just to get you started with the silicon. And if you need any help with your project, I'll be happy to answer questions in breakout rooms or after we finish the exercise. So first thing is you copy the example file into your Scratch directory, and you extract it to find the directory. Okay. So all the results you have, will be here. You have the script to submit. Yeah, and so in every case for the submit script, you need to add specific lines for the various parts of the code. Okay. The first thing we do is we do an SAF calculation to get the charge density for silicon. So this is simply a silicon and SAF calculation in the diamond crystal structure, so 2 atoms per unit cell, and we do a K grid that converts the charge density. The grid will not appear again later in phonon calculations. It's so in the 1-year calculations, because it will be integrated out as a charge density. Okay, so you copy this line to your submit script, and then you submit the job, and that should be very quick. Should take just a few seconds to complete. Okay. And once you have the charge density, you can actually go ahead, maybe the same script, do the calculation for the phonons. Now, the phonon calculation here is a very small one. We're just doing a 3 by 3 by 3 grid. That'll be the coarse grid that we start from. It's not meant to be converged. It's just to get a quick result, so you can start seeing results within the time we have for the tutorial. In practice, of course, you need to converge this number, maybe a 6 by 6 by 6 or 8 by 8 by 8. Something along those lines for silicon should be close to convergence. All right.
There is a question. Yeah, so Nirja is asking, is it possible to calculate the change in the band structure with your formalism? I think you mentioned this briefly yesterday.
Right, indeed. Thank you very much. Yeah, to answer your question, yeah, the answer is no. So this correction assumes that the band energies are fixed. They don't depend on temperature or the phonon. So there's no polarons, there's no temperature dependence in the band gap. So what you're looking at is just second order perturbation theory for the rates. So we don't update the electron energies, we don't update the phonon energies because of electron-phonon interactions. All we do is calculate the rate to go from an occupied state to an empty state through the assistance of the phonon. So the phonon here just gives momentum to light so that you can transition across the indirect band gap. Okay, so yeah, indeed, this is not something that we capture this formalism. But in principle, you could calculate the temperature-dependent band structure and enter that as your eigenvalue, or you could shift the spectra to account for the shifting band gap. That's what we do in the publication for silicon. That we had to manually shift the spectra to capture this temperature dependence of the band gap, which is the dominant term that matters here. All right, so you can launch this phonon calculation, which is a study for phonon calculation that we've done in the past. So you get your phonon frequencies and dynamical matrices. Excuse me. Sorry, sneezed, went away. And so yeah, with all your results for dynamic constants, you should, and because of the cubic symmetry, you should find a cubically symmetric dynamic constants for all your calculations. How do calculate the bands with GW corrections? That's a great question. So for the GW corrections, I would have to point you, unfortunately, to the Berkeley GW code website, because unfortunately that's a big chapter to do. Long story short, in a GW calculation, you would start from your DFT energies and DFT wave functions, and through the equations for the self energy, you will find an expression that corrects the LD energies using the LD energies and the LD wave functions. And after the whole process is over, you will have corrected again as the quasi-particle energies that do fix the band gap problem of DFT once you properly calculate the screening function, the self energy, and all. And unfortunately, it's a big chapter to address here. But if you're interested, I'll be very happy to point you to the website. The website, the code is the Berkeley GW code, also interfaced with Quantum Espresso. It's very efficient, very highly scalable, And I'll be happy to offer you hands-on help as well if you have specific questions about the code too. But unfortunately, there's not time to do this in this school. And thanks, yeah, for sharing the link with everybody. Yeah, please look at the link if you're interested to find out more about the code. But there are also many other codes that do GW corrections, like the Yambo code also works with Common Espresso. And so you have many tools that you could use to apply the corrections. Okay. And I mentioned back to GW because how to implement it here. What you need is this extra file that is provided with a tarball. It's the silicon.eig, si.eig file. And I will show it with you in a second. All it does, it shows the new eigenvalues for each K point and for each band in your 1-year grid. Okay, in your course 1-year grid. And once you have this information, the code will read the eigenvalues and interpolate them, just like interpolates the LD eigenvalues. Does that answer your question, Barbara?
No, yeah, I did actually GW calculation a long time ago, but I don't know how to put it there. So you mean instead in Espresso inputs, NSCF, you replace bands? Is this the step where you replace the band?
No, not yet. So we are still calculating the phonons. So we're not there yet. So to do Electron-Phonon, you first need your phonons, your wave functions, and then the energies. So there are 3 things we need to interpolate, right? Interpolate the phonon frequencies, interpolate Electron-Phonon coupling, and interpolate the electron energies. So electron energies is the one step that you need. And you will need the energy eigenvalues when you do EPW. So at no point do you tell the code, oh, please do GW here. We're not doing the GW within EPW. You have to do it separately and just pass a file with the corrected energies along the way. Here, Zhao has prepared the file for us, but if you need any help preparing for your system, we'll be happy to help.
Thank you.
Okay, thank you. All right, so once your phonon job finishes, just run the Python script, and that will create the safe directory for you, and you'll be ready to start your EPW calculation. A question about which value can have the bandgap value? Good question. So if your bandgap, it should be, either should have it. If you have a fine enough grid, you should be able to find from both. The trick with silicon is that the conduction band minimum is not on a high symmetry point. It's along the gamma X direction at a relatively low symmetry point. So you'd have to first do a band structure calculation to find where the gap is. And once you know the value for on a fine grid, then you know what kind of spectra to expect. So it's a good question. You would first need to know the landscape of the bands. You need to know what's the band minimum, the band maximum, and you have to go search for it. And that's a challenge. There's no other way to find the band extrema other than search for them. So what I'm saying is that if your gap is on a high symmetry point, you'll be able to find them on your coarse grid. Say in many materials like gallium arsenide, the band gap is direct and it's at the gamma point. So you will see it in your eigenvalues. In silicon, the conduction band minimum is on the low symmetry point. So it may not be part of your grid. So you'll have a point close to the minimum, but it won't be right at the minimum. So you need to first do an interpolation with 1-year, find where the minimum eigenvalues occur, and that will tell you what's the minimum gap, and that will tell you what is the photon energies you need for absorption. Yes, so you need a good 1-yearization to be able to find the band gaps accurately. So yes, you need to replace the eigenvalue 5 from GW, but the wave functions are still done from DFT. In the GW is still perturbation theory. So in first order perturbation theory, we update the energies, but not the wave functions. And in fact, that's one of the approximations we assume, but for most semiconductors, the GW wave functions differ by 1% or less from the LDA wave functions. So in general, it's a very good approximation to make that the wave functions don't change by much. While the bandgap may change by 50%, the wave functions change by 1% or so. So that's not a thing you need to worry about much for simple semiconductors. If you're doing systems where there's significant band reordering or band mixing or non mixing, maybe some bands get shifted more than others, then that could become an issue, in which case you have to look at a different starting point perhaps than the function that you chose to start from. Okay, great. So now we're ready to start the EPW calculation. All right. So I forgot the NSEF step. That's the full grid, the full 6x6x6 grid that we will use for the linearization process. All right, and now we're ready to do EPW. Okay. So we're doing silicon. Here's atomic mass. And here we're just setting up the files we need for the interpolation, right? Here's the I grid equals true. Now, so now the code will look for the file si.eig, silicon eigenvalues, right? And we'll try to read it, and that's where you will find the eigenvalue. So if you look at your directory, you will see this file that has the GW eigenvalues. Acoustic sum rules, and we set the parameters for the linear. It's a simple linearization for the silicon sp3 orbitals. If you're looking at higher photon energy, you may have to include more orbitals, like the d bands or so of silicon. So in principle, that number can increase by more than your valence bands. You can set some plot files. So you can also plot the bands to make sure you are getting a good linearization. So here we're just setting up the files for interpolation, right? So again, we replace in our submit script, we add this command, and should be for these parameters we set here. It should be a quick calculation. It should take about 1 minute. Okay. All right. So again, here's the flag about the I grid. Okay. So they ask the code to read an excess of eigenvalues, and here it is a set of GW eigenvalues that are provided from Berkeley GW. Okay. Are there any questions up to this point? So that's a standard calculation we do for all EPW, for most EPW problems, where we are at this point we are ready to start interpolating the Electron-Phonon coupling, the bands, and the velocity matrix elements. Right? That's where we should be. Okay. And also to interpolate, that's where we start doing phonon-assisted optics. Okay. So here's where we start. So welcome to our tutorial. This is where we start talking about phonon-assisted optics. So we do a restart calculation. We read the Hamiltonian, the velocity matrix elements, and the energies in the Wannier basis, and we compute the spectrum. So we interpolate to evaluate the expression we saw earlier, right? Now the K grids and the Q grids need to be quite fine. There's a question about the use WS flag, and maybe one of the developers can, if you could take a look at it, because I'm not sure about, I'm not fresh about all the flags and how they interact with each other. But here's the question we need to evaluate, right? This very fine sum over fine wave vector grids K and Q, and we need to interpolate the velocity matrix elements and the Electron-Phonon coupling matrix elements for all these K and Q points, as well as the energies, right? And the occupation numbers. Okay, so here's the input file, just to show you the key features. Again, now we are reading from the EPW files. So we're now reading the previously calculated quantities in the Wannier basis. All right, and here are the flags again. We're doing phonon-assisted absorption, right? So L index absorption has to be equal to true, this logical variable. The K grid has to be, we choose it to be in the reducible wedge, and we have to average afterwards, if you remember. And because the reducible wedge has a direction, while the spectra we're looking for is the, it has to be cubically symmetric, so we need to average the spectra. And here's where we set our window. The E Fermi read we set equal to true, and we set the Fermi energy to a value of 5.57 eV. Now that value is actually the mid-gap value from the GW eigenvalues. Okay, so once we know our band structure, we know where the events band maximum is, where the collection band minimum is, and we manually set our window to be in the middle of the band gap in order to ensure that we are capturing states only that in the energy window that matters for our spectrum. Okay. Again, we read the eigenvalues to ensure that we keep using the GW eigenvalues. And for the spectra, we need to set the spectrology where to sit in. Omega min, omega max, and omega step. Omega min, we set it to 50 millieV. We don't set that 0 because for 0 you get divergence. There is a 1 over omega pre-factor in front of everything, so it will make everything diverge. So if you set to 0, so we start at something that's not 0. The spectra should be, the epsilon2 should not have a value, should be numerically 0 until you hit the indirect band gap. So it doesn't matter where you start, and we stop at 3 eV, just before we go into the direct gap regime where divergences may occur. And we take a step of 50 millieV, so we take one data point every 50 millieV. So our spectra will have on the order of 100 data points in the end. Okay. And here's the window, right? Okay. So, all right. So here are the flags that are needed for phonon-assisted optics. dE Gauss W, that's the width of our Gaussians. Remember, we approximate every delta function by Gaussian. So we set it to be 50 millieV. So that will be the resolution of our spectra, right? In the spectra, we won't get any finer features. 50 millieV would be the finest feature we'll be able to see. But as you see in the answer, the final spectra are quite smooth. So this value should not be as important as, say, direct absorption, where you have sharp peaks or discontinuities and all. The spectra here are smoother. We set the temperature because we need to occupy the bands with phonons. Again, this temperature will not correct the band gap, right? It will not give you a temperature dependence for your band gap eigenvalues. This is only purely for the phonon terms, for the phonon Bose-Einstein occupation numbers, that quantifies how many phonons are there to absorb or to emit. And last but not least, the FS stick, that's the width of the window we're using here. Remember, we have our omega is 3 eV. Our phonon, we need to add maybe 0.1 eV for the phonons. We need to add, say, 5 times the Gaussian broadening. So we'll set to 4 eV just to be safe in this example. But for your calculations, you can be more aggressive and reduce the number even more to ensure you're not wasting any computing time if you have a very expensive calculation. All right. And here we're doing a simple interpolation. We go from a 3-3-3 grid for phonons and 6-6-6 for electrons. And then we go to a grid that's twice as fine, right? Go to a 6Q and 12K grid. And that's pretty much it. All right. So once you run this calculation, you should be getting your spectra. Okay. Again, the meaning of the flags, EPW read tells you to restart, indirect absorption enables the optics, and MPK mesh K use only reducible wedge. So that reduces the cost significantly, a factor of 48 for silicon. Please remember, though, you need to average the spectra in the end. And then omega min, omega max, and omega step are they describe the photon energy grid that we're calculating here. The Fermi level sets it to the middle of the gap. And then the spectra. Okay, now gamma is the broadening parameters we're using in the code, ranging from 1 millieV to 500 millieV in this log scale, 1 to 5 millieV, 10 to 50, etc. And in the end, your spectra should not depend sensitively on these parameters. Okay. When you are ready, you put this line in your submit script, you run it. Again, there should be a quick calculation. And you should get spectra that look like this. Okay. So you get a non-zero absorption in the spectral region between the indirect gap at 1.2 eV and the direct gap at 3.4. Now we have some absorption. So indeed, phonon-assisted absorption is happening with the code. Okay. You'll have two files, epsilon2, indirect absorption at 300 Kelvin. That uses the default Gaussian broadening, but you also have the files with Lorentzian broadening. Lorentzian has these longer tails. So it's up to you which one you want to use and what you want to compare to experiments. And these are the results you should expect to get. Of course, we're not converged yet. You see these dips here. That's because we don't have enough resolution to fill those gaps. There's an error in the code. I think K-maps. I think there's something with keyword. We can look at it again, please. Maybe another organizer can help with this question.
The K-maps input has been removed in the very last version, so you should remove it, I think.
Oh, maybe it was left in this input file. Probably. No, we've updated those. Maybe if you could use the latest examples from the workshop website, yeah, please copy this. If you are on Frontera, please use this command. Otherwise, please use the files on the workshop, the 2021 workshop, not the 2018 workshops, if that's what you are using.
Also, you need to use the special version of EPW.
Oh, I see.
Provided for the school. So if you are using, for example, the version from Quantum Espresso 6.7, then this will not work because some keywords have been replaced, have been removed. So you need to be very careful.
Right. Okay, so maybe it's the version because K-map. Yeah, so the code expects to read K-map. So yeah, it might be the version of the code.
Samuel, when this version will be available? Release with Quantum Espresso.
Yeah, so this is the version 5.4 beta because
I know.
Want to do more testing. So in principle, it will be released with the next Quantum Espresso release, which should be end of July, something like that.
Okay, thank you.
Yep.
All right. All right, and then once you converge, we're getting a spectra that look like this. And again, just a comment here, to go from the imaginary part of the electric function to the absorption coefficient, you need to multiply by the frequency omega, divide by the refractive index at that frequency, and also divide by the speed of light. So in the publication, you can assume a constant refractive index that's primarily controlled by the direct absorption across the direct band gap of 3.4. So once you do everything right, you should get a quantity with units of inverse length, and that's the absorption coefficient, how much light gets absorbed per unit length. If you converge it, you'll get smooth spectra. As you see, there's no bumps here, there's no peaks that increase as you increase the photon energy. Okay, so this is it. And if you want to look at the onset, you can look at that by focusing just in the region near the indirect gap, so network window, and the final K grid in order to see the discontinuity from the phonon absorption and the phonon emission term. All right, so with that, these are the steps we need to do. So the files are there ready for you, but we're more here to answer your questions, or if you are planning to run a project, we'll be happy to assist you with some decisions you may have to make along the way. So any questions for that? Where the polarization of the light enters? Indeed, so in the case of silicon, the polarization does not matter because it's a cubic crystal. But if you see at the equation, sorry for the scrolling here, hope I'm not making everybody dizzy. The polarization is here. If you look at my slide, this equation 1 for epsilon 2 is those matrix elements are vectors, and we're projecting them on the polarization of the light. So the matrix elements describe the optical transitions from valence to conduction bands. Those are vector quantities. And if you project along the X or the Y or the Z direction, you will get the spectra for the X, Y, or Z polarized light. If your crystal is cubic, just by symmetry, there is no such dependence. Whether light is along the X or Y or Z or any direction, there's only one spectrum you will get, no matter how you rotate your crystal or your spectra. In a crystal that's hexagonal, say Wurtzite, you may have different direction like in plane or out of plane, or rutile like titania or so. But this is where you will see it. So once you run the code, the output should have a directionally dependent spectra. And if I can stop, let me stop sharing this slide so I can share the command line. All right. So let me share the command line just to show you where you would expect to see. Here's the terminal. All right. Okay. So this is my Frontera. These are all the files you will get once you run the calculation. Oh, it's so I have all the APB. So I'm just going to focus on the EPW out here, right? Okay, so run EPW. If you go to the very end, you will get the spectra, right? So here's the spectra you will get. Okay. So this is the various levels of broadening you are using. This is the denominator broadening, the imaginary denominator. So here's for this photon energy, these are your spectra along X and Y and Z. And these numbers are 0 essentially, right? And the -8 is essentially 0 numerically. But when you go to photon energy around 1.2 or so EV, that's where you start see the absorption picking up, right? That's because we are reaching the gap of silicon, right? So yeah, you reach values. Remember, a value of 1 is very strong absorption, right? It's like a direct bandgap absorption. And so yeah, and in this code, remember, we're using the irreducible wedge, and that's why the spectra, say, along X and Y and Z are not the same, right? We have not averaged yet. So be careful here, because the symmetry breaking you see here is coming from the fact that we decide to go with the reducible wedge. If we're doing the full zone, we wouldn't have this issue, okay? All right, so, and here's the spectra, all right? So you see we reach pretty strong values, and that's why silicon is a good solar cell material, because it does end up absorbing strongly, even though it needs, not as strongly as other materials, but it absorbs decently, and you can give a solar cell that is not transparent. All right, so that's the one place you will find the spectra, but you will also find these epsilon2 files for Lorentzian and Gaussian broadening. So let me show you the Gaussian epsilon2 indirect absorption at 300 Kelvin. All right, so so here you see many values. Again, let me just to simplify it a little bit. I just want to show you the first few lines. Okay, let me clear a little bit. Okay, so the phonon-assisted absorption spectra versus energy. So the first column is the photon energy. In this case, the first point is 0.05 eV. And then we have the spectra for the various choices of the imaginary denominator, right? And remember, a spectra should not depend on the imaginary denominator. The first point is the 1 millieV broadening for the denominator, 2 millieV and 5 millieV, 10 millieV, 20 and 50, and then 100, 200, and 500. Of course, here they're all 0, so you don't see any variation. And for each of these imaginary denominators, because we're doing silicon, we have already averaged along the X and Y and Z direction. Okay, so we're assuming we have a cubic crystal for this exercise. If you have a different situation, we'll be happy to help you modify the code and adjust it to your situation. But if you look at the spectra, so say, and let's print just to see the first two data points. So here's what you would see. Say if you use it for the first broadening, right? The photon energy, and here's the broadening parameter. Just to show you, here's let's look at two different broadening parameters. I use 1 millieV or I use 2 millieV. Do I see a difference? And as you see, I should not see a difference. And indeed, look at the situation here, right? The values are almost exactly the same, right? That's what should happen. It means that the imaginary denominator does not affect my results. That's a good sign. Okay. The problem is if the broadening becomes too broad, say now let's compare the 1 millieV data with the 500 millieV data. Now we should start seeing differences, right? Because having such a large denominator broadening, it starts to affect the energy. So you see difference here, the order of, excuse me, 10%, 20%. So, so when you plot your spectra, you need to make sure that you don't see this sensitivity to the broadening, and that's why the code outputs them all. So when you plot them, you compare to each other, and you see. So for each line here, you have the photon energy, and then the spectra for 9 different values of the imaginary denominator that span a very broad energy scale, for 1 MeV to 500 MeV, just to make sure you don't have any sensitivities. All right. So that's pretty much it. If you have any questions, I'll be happy to answer about your specific projects, if you're somebody, this is a tool that you are using. And I also like to point out to Friday's discussion, tomorrow's discussion by Marius, who will discuss an alternative method on how to calculate phonon-assisted spectra using supercells and embedding those phonon displacements in your starting mean field solution. So you will make a supercell, you will move the atoms according to a specific pattern that he found that will correctly capture all the phonons that you, of your system, and we're able to break the symmetries and give you the phonon-assisted spectra as well. Okay. So again, the two methods, if you're focusing on a narrow spectral region where only a few wave vectors and a few bands matter, maybe the code by perturbation theory is more efficient. If, on the other hand, you want to capture all phonons for the entire Brilliant zone, and maybe Marius' method may be the way to go, because it also captures the temperature dependence of the band gap and Urbach-Tell and other features. All right. Everybody was able to run the code successfully. Are there any questions about running the code?
Maybe we can ask Fatima, is it working? Because she said that she has an error still with the EPW2. Maybe, I don't know if she can unmute herself.
Yeah, Fatima, if you have a problem, I would say maybe if you turn off the breakout rooms, so you can set a breakout room with Jao or with Kyle, maybe if you can share your screen, they would be able to look at your output.
She said it's okay, it's working for her now.
It's working? Okay, great. Thank you.
There was one question that I think you didn't answer.
Oh, sorry, please. Okay.
No, I have to go back. Yeah, it's from Barbara. Yeah, it's what option should I put in Quantum Espresso with GW correction to get the correct format for the EIG file?
So the format of the EIG file, let's look at the EIG file.
So first of all, you cannot really compute GW just with Quantum Espresso. We should,
right.
Well, yeah.
Yeah, exactly. Yes, I forgot to mention that. Yeah. So yeah, I just want to talk about the format. So the file, if you want to do GW corrections with Berkeley GW, then Berkeley GW will prepare the file for you. Okay. So if not, what you will do is the following. You have a file that should have the bands for each K point on your coarse grid. What is the coarse grid? In this case, if you look at APW1, your coarse grid is the 6 by 6 by 6. So you will have a 6 by 6 by 6 grid on which you need those points. And how many bands you have? The bands we're using, we're projecting out 8, the NSCF.in, that is 12 bands. So you need 12 bands on a 6 by 6 by 6 grid. So let's see if that's what you have in the silicon.eig file. So here there are 12 bands for 216 K points on a 6 by 6 by 6 grid, right? So the code, these are the GW gaps. For example, you will see here that the direct band gap, this is the gamma point. So you go from 4.9 eV in the valence band to 8.2. The absolute numbers don't have a physical meaning yet, of course, but the relative magnitudes matter. The gap here is 3.3 eV, which is very close to the direct band gap of silicon number, 3.4 eV. Okay, so you see this has been corrected with DFT. On the other hand, if you look at the NSCF.out, you still get eigenvalues here. Oh, actually, we don't print them. Sorry for that. But the eigenvalues in the NSCF.out do not have the GW corrections, and the band gap is underestimated by as much as 50%.
So I also
right.
can do scissor operators, yeah? Manual, to do it manually, yeah?
You can do that. You can do that too.
In Excel file, and actually I can use even my custom code. I can do any bands, you mean?
You should be able to change the eigenvalues in any way you want. Now, if it's just a simple scissors operator, maybe something similar you could do is instead of adjusting your eigenvalues, you could just adjust your spectra. Say, you say your band gap is underestimated by, say, 1.5 eV, right? I'll give you an example here. You can still do everything with your underestimated gap, and then in the end, take your spectra and shift it by 1.5 eV. Right, that should be equivalent.
And this will affect my relaxation time. If I modify those bands, would relaxation time be affected?
The relaxation, I suppose you mean the rates for optical absorption?
Or for example, if I do something like this modification in band structure, and I want to calculate conductivity.
Conductivity.
Then it would make effects or not?
If it's a rigid scissors operator, meaning you just increase the gap, but you don't change the band curvatures, then the scattering rate should be.
This won't. But I mean, if I change my band structure, would it affect my relaxation time?
It depends on how you change it, right? If you change the curvature, then yes.
Yeah, so it is going into calculation, yeah?
It is, yes, of course.
Okay, thank you.
Yeah, if you use the read eigenvalues, then the eigenvalues on the fine grid will be the replaced ones. Indeed, so any change you make to the eigenvalues that you read will be applied to your final results. Yeah, but if you have a rigid shift, because the curvature is exactly the same, you should get the exact same relaxation rates. It should not depend on them.
Yeah, it will be the same. Yeah. Thank you.
Exactly. Welcome. Thank you. Did I miss a few questions? Oh, sorry. Jean made a good point that one of the flags in the instruction is not used anymore. The EP temp. Sorry for that. Maybe let me fix that. Sorry. Maybe. So the correct one is the one in the file, right, Zhao? Do you understand correctly?
Yes.
Yes, all right, please, thank you. So let me share again, sorry. All right, so if you want to look at the temperature, this is the flag you need to use, temps. So please take a look at Zhao's comment. So temps is the flag you want to use. Okay. And thanks, Kyle, for sharing also the link to read more about the code. Okay. And Simone has a question that indeed you can provide multiple flags, right? So the temps can be a list, if I understand right. Is that right, Jean-Carl? You can just put a series of strings and the code will do for all of them. Is that right?
Yes. So essentially what you can do is to provide multiple temperatures here, and then the code will actually output the epsilons for each temperature in a separate file.
Got it. Yeah. Fantastic. All right. Is there any question I missed? Yeah, actually, indeed, the temperatures is another flag here. And the temperature, again, I just remind everybody that this is only used for the phonon occupation numbers and not correcting the band gap in this part of the code. But you might as well introduce this correction after the fact. Once you know how the gap depends on temperature, you can shift your spectra to match that temperature change of the band gap. So that's something you can do. All right. And as always, we'll be here today and tomorrow as well. If you have any questions, if something you want to use in your project, we'll be happy to help as well for your specific situation. All right. So yeah, so this is for the, if there are more questions, this is it for the phonon-assisted optical part. We'll stay around, me and John and Kyle, if you have any questions that you'd like to ask, maybe individually in the breakout room. And we can move to EPW, to the superconducting module of EPW if everybody is ready for that as well. Yeah,
I think the plan was at 30, but so if, I mean,
go 30, okay, sure.
It's okay. I mean, if Roxana is ready, but we can also wait 2 minutes more to see if some questions are coming.
Okay, great.
Otherwise, yeah, we can either wait 30 or 2 minutes before.
Okay, that sounds good. Yeah. All right. Yeah, I'll stay available for questions. Yeah. It'd be nice also to see a parallel with Marius's version, Mario Zacharias' method on Friday, because you have two different options on how to look at the phonon corrections to the spectra. And depending on your project, one method may be preferred over the other that will help with the computational cost and capturing the correct physics of your problem.
I want to confirm that I understand this. So actually, because this is a special grid in EPW, so I should use NSCF grid, yeah, for GW.
Precisely. You want the GW eigenvalues on the same grid that you're going to interpolate from, precisely.
So what we have in NSCF input file. Yeah.
Precisely. Because and sometimes, in this case it is 6 by 6 by 6, but in some situations it may not be fine enough. Maybe you have to go to 8 by 8 by 8.
Yeah.
In that case, you would have to also have GW on the 8 by 8 by 8 grid to interpolate from. You're absolutely right.
Okay, thank you very much.
Thank you.
Just to add one thing, so in general, GW code are able to use crystal symmetry. So you don't really have to force the GW code to do 216 points. You can use symmetry, because otherwise it's going to make the GW calculation expensive. So you can simply compute the eigenvalues on the irreducible wedge and then copy it manually. I mean, you can do both. You can ask the code to do all, but maybe a more clever way would be to just do it in the irreducible Brillouin zone, and then you copy by hand, and then you feed that to EPW just for computational cost.
Indeed, yeah. I want to share. I'm mostly familiar with the Berkeley GW code, and that code, yes, will automatically. There's a script that will automatically generate the full grid for you after calculating only for the reducible grid.
That's very helpful. So I've done it with Yambo, and it doesn't do that. Yambo only reports on the irreducible grid. So I had to do it myself. But okay, it's very useful. Okay.
Yeah, it's quite handy to have a tool that can do it. Yeah.
Yeah, I probably might be lazy and use my custom code.
Yeah, but even a simple scissors operator is already doing great. You may capture some finer features of the curvature, but by far the most important is to get the band gap right, because that really determines the onset.
Yeah, for absorption, yeah.
Exactly, yeah. I would say if you have to correct one thing, the band gap would be the number one to correct, and the curvature is second order.
You don't need to use GW. You can use B3LYP. It works very well.
You can use pretty much any method you want. You can use hybrid functionals. You can go to experiment if you wish as well. Indeed, and I would say the simplest way is, if your mean field solution, whether it's LDA or PBE, if it has a band gap, then you will see the band gap, and then you can just shift your spectra to
Okay, thank you very much, Manos.
Thank you, everybody.
I think now, we can switch to the second part presented by Roxana on